in only two different indeterminate cases. Indeterminate cases. A total of 7 indeterminate cases. But only in two situations, 0 over 0 or infinity over infinity. You remember that every time we determine a limit, we have to plug it in to identify if this is a number or is an indeterminate case or what is it. So when we plug in A and we get 0 over 0 or infinity over infinity, we are allowed to calculate the limit, continue, sorry, limit as x approaches A from either side from P prime of x over Q prime of x. Notice that without the limit, I will never, ever say that P of x over Q of x prime is P prime over Q prime. That would be a terrible mistake because I have to use the quotient rule. But only inside a limit. So inside the limit and only inside the limit, if it's a rational function or whatever, but I can show that it's a indeterminate case, either 0 over 0 or infinity over infinity, no other situation, then we can proceed to find the limit by simply differentiating the top and differentiating the denominator. So I would like to look at a couple of examples, and they are on page, if you'd like to open the multimedia library, they are on page 175, from problems 75 through 84. 175. Okay. Let's say I will start with 80. You can choose, feel free to choose. So we have limit as x approaches -4 from x squared plus x minus 12 divided by x plus 4. You can say this is a piece of cake. When I plug in 4, I get 16. 16 minus 4 minus 12 is definitely 0. 4 minus 4 is 0. Why don't I just factor? True. But I want to use the L'Hopital's rule because it's one of the indeterminate cases in which I'm allowed to use L'Hopital's rule. So then I copy limit as x approaches -4 from either side. I differentiate the top to get 2x plus 1. I differentiate the denominator to get 1. And now I plug in. 4 times -2 is -8 plus 1 is -7. And I don't need to factor anything. That's it. But it only works in the two indeterminate cases, 0 over 0 or infinity over infinity. Would you like to choose another, or we go back to chapter 2?
Hirsch, can you hear me?
Yes, perfectly. Yes, okay. Hirsch.
Can we do number 84?
With pleasure. Let's do 84. So we have limit as x approaches -infinity. The top is 3x cubed plus x plus 11. The denominator is 6x cubed plus x plus 2. Good. When I plug in infinity or -infinity, these 4 terms don't count. Too small to mention. They don't exist when I plug in infinity or -infinity. Otherwise, they do exist. So this goes to -infinity. This goes to -infinity. So it's infinity over infinity. We are lucky. We can use L'Hopital's rule because it's one of the two indeterminate cases. So we go on by differentiating. Top, x approaches -infinity. The top will be 9x squared plus 1. The denominator prime will be 18x squared plus 1. At this point, I plug it in again. Of course, not here. I get infinity over infinity. That's fine. I will apply L'Hopital's rule again. The top prime is 18x. The denominator prime is 36x. At this point, I am allowed to simplify. Here I cannot. I cannot simplify. And the answer is 18 over 36, or 1 over 2, which actually I knew from the very beginning, because from pre-calculus, we teach our students that if these two have the same degree, when x approaches infinity or negative infinity, we get a horizontal asymptote, which is the leading coefficient over the leading coefficient. I knew from the beginning that 3 over 6 will be 1/2, but I wanted to use L'Hopital's rule. Very good example. Do we have other questions? Do we need other problems here, or more examples, or we move on, we go back to chapter 2? Okay, so let's go continue with 2.2. So that was L'Hopital's rule that I omitted by mistake, so sorry, I forgot. It's in 1.8. So I'll make this part of the next exam. Okay, so we go back to 2.2. We basically talked about how we identify max min, but we just need to practice. We didn't have enough examples. So on page 217, this time they're asking us to graph the function. No, we are not ready to graph any function yet. But we are asked to look further and find the points of extrema. And then we're going to look at the second derivative. And I'll explain why and what does the second derivative tell us about the function. Okay. So on page 217, I'm going to choose the first one, and then you choose the next one. Let's say problem 11. Oops, that's not a good color. 11. So in 11, we have f of x equals 2x cubed minus 3x squared minus 36x and plus 28. First step, we would like to determine critical numbers. I cannot determine critical numbers before I find f prime. 3 times 2 is 6, subtract 1 from the power. 3 times 2 is 6, subtract 1 from the power, and minus 36. And when I differentiate 28, I get 0. So I know that critical numbers come from f prime being undefined. There is no such thing. It's a polynomial. The second possibility, from f prime being 0. Good, that's possible. 6x squared minus 6x minus 36 equals 0. Of course, I will divide both sides by 6. And I get x squared minus x minus 5 equals 0. I will continue. Of course, it's 6. I'm sorry. Got distracted for a moment. So x minus 3 and x plus 2. I was just thinking because I looked at it and I said, oh, it's factorable. But then I wrote 5 instead of 6. Okay, so x equals 3 and x equals negative 2. So these are the critical numbers. We get our table going. And in the table, we are going to put f prime of x as the first row, f of x as the next one. Of course, the first one is all the domain of the function and the x values. And then we're going to talk very shortly about the second derivative and what does it tell us. Okay, so we'll continue by finding a domain. And I know the domain is all real numbers. It's a cubic function. It's a polynomial function. There is no discussion there. 0 must be in the table anytime, even if the function is undefined at 0. And now I have a negative 2 where the first derivative is 0. I have a 3 where the first derivative is 0. And I'll get my calculator and plug the function, the original function in to determine the y value. When x is -2, what is the y value? When x is 3, what is the y value? So in y equals, I clear whatever I have, and then I have 2. I enter 2x to the third, and then minus 3x squared, and then minus 36x, and then plus 28. Making sure I put it correctly, yes. Second and table, and I only want -2 and 3. -2 and 3. And I got 72 and -53. At this point, I'm ready to determine the sign of the first derivative. So I'm ready to put in the numbers in here. If you want, well, let's also plug in 0. So this is 28. And we can also determine the end behavior of the function by finding the limits. Let's do just that as well before we find the sign of the first derivative. Limit as x approaches -infinity from 2x cubed minus 3x squared minus 36x plus 28. And the same thing for limit as x approaches infinity from the same thing, 2x cubed minus 3x squared minus 36x plus 28. Well, we notice that when we talk about infinities, these do not count. Nothing here. Waste of time, because they are too small to mention. This is the most powerful. If I determine x approaches the limit when x approaches 5, everything matters. But when we talk about infinity or negative infinity, nothing matters but the most powerful term. When I plug in negative infinity, this will be negative infinity. When I plug infinity, this will be infinity. Perfect. So now I go back, finally, back to the first derivative. I'm going to copy it here as 6, x minus 3, and x plus 2. This is the best form for what I'm trying to do now. Or you can just plug in numbers. So,
can you move the paper up a little too?
Like this?
Yeah, that's good.
Thank you. Sorry about that. So now we have to find the sign of the first derivative and make sure that the sign of the first derivative and whatever I have already in the row for f of x, they go well together. If they don't, I'll say oops, and I have to go back to the drawing board. So let's give it a shot. So for -10, this is negative. -10 plus 8, this is negative. Everything here is positive. The product is positive. When I plug in 0, I get negative. When I plug in 100, I get positive. So now this is the moment of truth. I'm trying to make sure that these two work well together. From -infinity to 72, the function is increasing. But is that supported by the sign of the first derivative? Yes, it is supported. It's increasing. From 72 to 28, it's decreasing. And that's exactly what the first derivative, the sign of the first derivative is saying. Same thing from 28 to -53. But from -53 to infinity, obviously, it's increasing. And it's true, and it's supported by the sign of the first derivative. Obviously, -2, 72, because the sign of the first derivative is positive, 0, and negative, this must be a local max. This one, 3, -53, must be a local min. How do I know? Simply because the derivative is 0 or undefined, and it changes sign from negative to positive. Same thing for the local max. the first derivative is 0 or undefined, not undefined in this case, but it could have been undefined. And then the sign changes from positive to negative. Okay, in the next step, I would like to look at the second derivative. Why? In a minute, you will know. So let's find the second derivative. And of course, I'm not going to differentiate this because I should differentiate this. This is much easier. 12x minus 6. At this point, I will set the second derivative equal to 0. And I'll explain why. So let's find x equals 6 over 12. But I'm going to simplify it to 1/2. I will go back and put it in where it belongs, 1/2. I will find this number, the y coordinate of 1/2. Back to the graphing calculator, I still have the function in second and table, and I put 0.5, and I get 9.5. So this value here is 9.5. Okay, let's discuss what this means. If the second derivative is 0 at a point, I'm going to call it C, or x value C. If f prime of C is 0, C could be an inflection. Of course, C comma f of C, maybe that's better because I'm talking about a point. C comma f of C could be an inflection point for f of x. What does an inflection point mean, first of all? It means that the function is either concave up, opening upward, and then all of a sudden at this point, it starts opening down. This is what we call IP, inflection point, from concave up to concave down, or vice versa, from concave down to concave up. This is still a point of inflection, where we say the function changes concavity. So at the inflection point, f of x changes concavity. So what's the difference? When the function we say it's concave up, some people say it holds water. The second derivative is positive. If it doesn't hold water, all this piece, all this territory, for this area of the function or part of the graph, the second derivative is less than 0. And why is that so important? It's important when I graph it. We're not there yet. What else can I learn from this? And I'll go back in a moment and I'll show you. So the second derivative must change sign. If the second derivative does not change sign, that is not a point of inflection. So I have to study the sign of the second derivative now. So I go back, I put at 1/2, this is 0. The second derivative is 0 at 1/2. That's what we got. Second derivative is 0 when x is 1/2. And the second derivative is a linear function with a positive slope. So what will be the sign of such a function? From negative to positive. Negative to positive. Or just plug in a number. So on this territory between negative infinity to 1/2, when I graph it, when I get the chance to graph it, it must be graphed concave down. And from 1/2 to infinity, the function must look like this. It must be concave up. If it isn't, something is terribly wrong. Again, I have to go back to the drawing board from scratch. So now, Studying the second derivative allows me to find the inflection points if they exist and find concavity. So two things, the inflection point and concavity of the function. What else? Okay, there is a third thing that we learn. Don't change anything. I'm going to make some changes, but I will put them back. So don't change anything. So where are we time?